Hey there, everyone. Today I have a very interesting topic. I want to compare random forest versus TensorFlow versus PyTorch and see which model is capable of making better predictions. So TensorFlow and PyTorch usually outperform a random forest regressor in scenarios where there's very complex patterns that need to be learned or dependencies that are challenging for a human being to understand just straightforward in a typical column and row structured data set. But regressors, specifically random forest, XGBoost, there's a bunch of regressors that tend to outperform their deep learning counterparts, specifically TensorFlow and PyTorch, if the data set is smaller, less complex, structured, and pretty straightforward. Okay, so deep learning is great for image recognition, things like natural language processing, speech recognition, time series forecasting. It's excellent when you need to work with unstructured data, which could be data coming from streams of sensors, audio, visual, something like that, very unstructured. Any kind of classical machine learning algorithm isn't going to perform very well in that type of environment, but deep learning algorithms will. Any kind of transfer learning is perfect for these generative tasks like Gen AI. You see this with ChatGPT. That's all deep learning. That's fantastic. But sometimes good old-fashioned classical regressor can outperform these more sophisticated supercharged deep learning models. So let's take a specific use case right here. We'll jump into it. So I have all the code set up. This is the classic empty cars data set. I'm covering this in a lot of my videos. I think it's very generic, very easy to understand, and applicable for many different regression scenarios. But and it's very easy to work with, but I want you to envision your own specific data set and substitute that here. I'm just using this just to illustrate the point of what's being done, but this is just a fun exercise. It's not exactly practical. I would expect you to substitute your specific data set for this one. So let me go ahead and refresh this, do the import. Okay, we can see a few features here. Miles per gallon, number of cylinders, displacement, horsepower, so on and so forth until carburetor, right? And the row names are the names of the cars. So we are going to use these numerics as independent variables. So everything that's an X variable is independent, and anything that's a Y variable is dependent. So we're trying to take all of these independent variables right here that we're assigning to the X variable and try to make a prediction of what the miles per gallon should be, given all of these features that we feed into the model. So we are doing number of estimators is 100, set the random state to 42, and what is this? Test size is 2, so training size is 0.8, right? We always have a training size of around 0.7, 0.75, 0.8, and the balance goes into the test side, right? So we need a holdout set to be able to make predictions against and see how accurately the model is coming up with predictions against the actual test size that's being held out here. So let me control enter this cell, refresh it to run it. Okay, so the model is making its predictions. This is the important part right here. So for cylinders, let me take a step back here. What got printed? Let me check this out real quick. Okay, mean absolute error is 0.168. That's pretty low. If you get 1, 2, 3, that's pretty low error. Closer to 0 is better. That's pretty low error. So this model is going to make very accurate predictions. Here is the fitting of the model right here. And we just called model as model, random forest model as model, right? So those two link up. And we are going to use that model to make predictions against the X test set, right? So we have the training set, which is 80%. The test set is 20%. Here's our predictions, okay? Now, once we have the predictions, we can go down here and use predictions right here to get the mean absolute error, okay? Now I'm creating a new data frame with cylinders equal to 6, displacement 160, horsepower 110, so on and so forth. Then we have 144. And if we go back and look at the first item in our data frame, we have basically the same data, right? 21, I'm sorry, starts here. 6, 160, 110, 144. 60, 160, 110, 144. That's what we have here. 6, 160, 110. We have the middle guys and 114. We make predictions, right? And I want to see how accurately this model is able to make predictions. It says that the printed value is 20.82, and we know that that value, miles per gallon, should be about 21. So if we do 21 divided by 0.82 minus 1, the model is off 0.86%, so less than 1% error. So this is about 99% accurate. So the model is very, very accurate, right? We can put in any kind of variables for this array right here, okay, and be able to make a prediction, and we're going to see how far we are off from the actual value right here. So if I scroll up again, you'll see Mazda RX-4 is 21, right? Given all of these independent variables, we would assume MPG to be 21. The model calculated 20.82, so pretty close. Very, very accurate predictions, right? Let's do the same thing using TensorFlow, okay? And then we'll repeat the exercise one more time using PyTorch. I'm going to do Control-Enter to run this, okay? And I'll step through the high-level code. I'm not going to work with every single detail and every nuance here because the video would be way too long and it would just drag on for hours and hours. And I don't think that would benefit myself or anyone in the audience here. So I'm going to keep it pretty tight and crisp, but I am going to share all this code. I'm going to save this as an HTML file and upload this when I upload the video to YouTube. So you can download the file, double click it, open it, and you'll have access to all the source code. So you can copy and paste this into your own Jupyter Notebook environment, run it, you'll get the exact same results. And of course you can break down the code, tear it apart, peel back the layers of complexity and see how it works, then put everything back together again. And I think it's going to be a tremendous learning exercise. So let's go down. The model ran. Let's see, it's doing 50 epochs, and epoch is a loop. So basically 50 testing iterations to be able to make a prediction. Okay, so let's make sure everything came out straight. Okay, it's saying predicted MPG 15.68. So let me update this. I ran this before. The prediction is slightly different. I'll change it every time, but not by too much. 15.68. 68. Whoops, 68. Fat finger the key. I'm going to subtract 1 to get this into a relative percent. Okay, so let me go to Excel, pop this in, and get a new sheet here. And we have a slow mouse here. We have a new sheet coming up. Okay, enter. 33.92. Okay, so this model is off 33, almost 34% of the time. It's going to make bad predictions. So that's horrible, right? Like 33.9. That's what I saw, 33.9. So it's not very accurate learner at all, okay? And that's okay. We tested it. We trained it. We looked at the predictions. And again, the predictions now are coming from right here. So the step is slightly different with these deep learning models. We have to set up an array and then make a prediction on the array. We have new data. These are the independent variables, right? We have the new data TensorFlow. That's how I'm abbreviating it here. And you'll see new data TensorFlow being fit into this predictive model that was just trained and tested, right? And it's not accurate 33% of the time. It's accurate 67% of the time, or 66, whatever you want to round it off to. Okay, let me do one more example. And again, it's totally fine. We have a very structured column row sort of data set, so the RandomForest Regressor is going to perform much better in this type of environment. If you had very complex data set or hundreds of features, maybe no relationships, maybe a convoluted neural network or something like that, then PyTorch and TensorFlow are going to shine. They're going to outperform the classical regression algorithm, right? But in this case, when everything is just so simple, the algorithm in the TensorFlow world and in the PyTorch world just can't resolve it. It just can't make those kind of reconciliations very accurately. So again, I'm feeding in the independent variables, okay, to a new data array called PyTorch, new data PT, and then I'm fitting that into the model and making predictions. And this said 14.39. Okay, so I ran this earlier just to test the code, just refreshed it now. So 14.39. Okay. So let me put that down here, copy paste. And we'll update this. I mean, it's going to be pretty similar, but it's going to be slightly different, right? Boom. And get this, copy paste it. So we know that MPG should have been 21. The model predicts 14.3. So we're really coming up short here. Really not performing well at all. Pop that in there. Enter. 45% of the time it is making bad predictions. So 55% of the time it's accurate. So that's pretty horrible to learn, right? So 45, I'm going to update this right here. Okay, yeah, that's a bad learner, but that's fine. We ran the exercise, we got the output. It's very enlightening, very interesting to see how these neural network models perform next to a classical regression model, right? You have to use the correct model for the job. That's the point here. And I wanted to show you how to do predictions too. That's why I'm setting up the model training, testing the model, and making predictions. I've seen a lot of videos all over the place where people are training, testing, they get their R score or F1 or accuracy or RMSC score, and that's it. They just stop there. But I don't understand that, because you really should be training the model to make predictions into the future. What's going to happen next? Like, it doesn't end with the training and the accuracy or the precision or the R squared. That's great, but the next step is to use it to make predictions. So I just mentioned it because I've seen a lot of videos where they stop just 1 meter short of where you need to be. The whole point of running these experiments is to train and test the model, of course, but to make predictions as well, right? That's really where the rubber meets the road. So that's the most important thing. So I have a couple more notes down there. I'm going to save this file, post everything in this file with all the business logic, all the data. When I post the video, it'll probably be later today. So you'll have access to all that. Again, I don't have time to go into every nuance and every detail, and the video would drag on and on and on if I did that. So I'm going to stop it here. We illustrated the point. We proved what we needed to prove, and I think this was successful. So yeah, hopefully you guys learned a thing or two today. Thank you so much for your time, and have a wonderful day. Bye.